Hmm. Hi TJ.
Hey, Udit, how's it going?
Good. How are you? Long time.
Good, yeah, it's been a while.
So
How's the conference going so far? I
it's
was
going
able to
very,
watch a couple of the talks on YouTube today. It seems really cool.
oh, very nice. Yeah, it's going very well so far.
That's good.
Yeah.
Good, good. You guys got some really good speakers, it looked like.
Yeah, yeah. I mean,
Hi,
like speaker
TJ.
lineup is really good this time.
Hey, Udit, how's it going?
Good. How are you? Long time.
Good, yeah, it's been a while. Oh. Yeah, Udit, I'll be talking mostly about my more recent work at NASA.
Yeah,
Um,
that's good.
Basically along those lines. Not so much on the climate stuff that I was doing before.
Yeah, sure. So would you like to do a quick screen share check before I start the webinar and people may start joining in?
Yeah, let's try.
Yeah, I can see your slides. All right, perfect. So
All
I
good.
will I will start the webinar so that people can join. You may keep your slides on so that people can read the first slide or title.
Okay, cool. Yeah, I can leave it here.
Sure.
Do you see it right now or
No.
okay? Yeah, I stopped it. Let's see.
Yeah. All set. So I'm going to start the webinar.
Awesome. Hi, Mayank. Hello. Yeah, hi. I think Udit.
Hi, hi, Abir.
Yeah, yeah. So yeah, I just joined. So we'll start at 8, right?
Yes, yes, Abir.
Okay. Thanks a lot. Yeah. Hi, Thomas.
Yeah, I was trying to unmute while being sharing screen.
Yeah. So should we start?
I'm ready.
Okay. Yeah, I'd say. So Udit, what do you say? Should we start?
Yeah, I think let's go, Abir. Let's go
Okay.
ahead, Abir.
Hi. Okay. So let me introduce our speaker for today. So first of all, good morning, good afternoon, good evening, as applicable to different parts of the globe. We will be having in this session first Dr. Thomas Vandal as our speaker. So he's a research scientist at the NASA Earth Exchange NEX at MS Research Center and Bay Area Environmental Research Institute. So he received his PhD in interdisciplinary engineering from Northeastern, and before that, a BS in mathematics from the University of Maryland at College Park. He is currently a PI in NASA's research program for geostationary satellites. And his research interests include machine learning, computer vision, and data mining for applications to climate science and remote sensing. So he will be talking about a machine learning system for Earth observation. So Thomas, to you.
Thank you very much for that kind introduction. And thank you for the organizers. It seems like a really interesting conference you guys are putting on. So today I'm going to talk about some of the work my group has been doing at NASA Ames and NASA Earth Exchange, mainly looking at certain type of geostationary satellite imagery. We'll get into what that is and kind of all the Earth observations behind what NASA's doing. This work is in collaboration with a whole bunch of people at NASA Ames, at Goddard Space Flight Center, Microsoft Research, and Northeastern University. So Earth science at NASA is about, I think it's somewhere around 25% of NASA's budget. So we're trying to, so the Earth Science Division missions are trying to help us understand our planet's interconnected systems from a global scale down to minute processes. So this is from climate models, which are going to be ran for 100 years, to local scale effects that could be at 30 meters in the meter kind of scale, right? So what's happening right now? So there's a whole kind of mix of data that we're interested in observing. So we collect all this data, measuring atmosphere, land, and oceans with kind of varying sensors, which we will discuss. And all this data that NASA generates is publicly available through LPDAC services and us actually at the NASA Earth Exchange also. So what the NASA Earth Exchange does is we bring together most of the NASA Earth Science data sets onto the Pallades supercomputing system at Ames. And we basically enable scientists to come to us to work with the data, since the data is so big. So to give you a sense of the size of the systems we're working on, we have about 11,000 nodes on our system at current, with over 240,000 CPU cores on there. And we keep adding GPU capabilities and other high performance computing capabilities too. NEX itself, we maintain 4 petabytes of data storage. This can multiple levels. So this includes observations, model outputs, and meteorology data sets to be used by the community. So a lot of the times when NASA projects are funded, you can request to get access to the NASA Earth Exchange as part of that grant, and then we help them work with the data from there. So my interest at the NASA Earth Exchange is basically using machine learning to make the best use of this data. And I'll talk about the data a bit more for a couple more slides to kind of motivate some of the problems that we're looking at. I think a lot of the machine learning stuff that I've been developing has been less like straight methods focused and more kind of looking at the data and figuring out what methods we should use for that given problem and for that given data set. So NASA itself currently flying, I think, more than 20 to 30 satellites, with more planned to go up in the future. These satellites will stay up between, say, 5 and 10 years. So generation after generation, we can continuously improve these satellites. The data generated from all of these processing that we do, all the observations that we get, it's increasing exponentially, and is honestly making it quite challenging for us to work with and store. Even working with many of the cloud providers, there's been kind of some questions on what we're gonna do with all this data that we're generating. So the range of data sources that we have to work with include really three main categories: satellite observations, physical model simulations, and ground-based observations. So we're going to talk mainly about satellite observations here. And this can include anything from optical sensors, so RGB, near infrared, infrared, microwave, hyperspectral, radar sensors, LiDAR, and so forth. There's many different orbit characteristics that generate different spatial and temporal resolutions that are applicable to different problems, scientific problem domains. So on the climate scale, we may be interested in looking at data over a 20-year period, where we have some observations over that length of a period, but they're not going to be frequent, they're not going to be high resolution. And the more modern data sets that we have, if you're looking at kind of a weather application, we want to be looking at real-time information that we can process at a high resolution. So there's a whole range of data sets here. A lot of these observational data sets go into physical model simulations. So this could include climate models, which we're running out to 2200 to kind of understand climate change and climate adaptation practices. These observations are also put into data assimilation systems and forecasting for numerical weather prediction and in near real time. So at GeoNext, at the NASA Earth Exchange, we have a big project going on right now on using geostationary observations. And geostationary observations give us a high temporal frequency. They stay in one location above the Earth and they orbit with the Earth. So due to that orbit, they're able to stay in that constant location and take really high frequency imagery, though it's at a very high altitude. So we do lose some spatial resolution there, but we get this near global coverage of 16 spectral bands. This includes visible, near infrared, and infrared, which allows us to monitor all different types of physical processes. So currently there are 3 to 4 satellites up there, modern geostationary satellites. And 2 of these are ran by NASA and NOAA, GOES 16 and 17. So those cover the eastern and the western United States. Himawari 8 is a Japanese sensor that has pretty similar specifications. And then there's satellites from the Koreans, the GeoCompsat 2A, and Europeans have one, and then the Chinese also have one. So we're getting to a point where we almost have this kind of global coverage of geostationary, which is really enabling 10-minute global observations of the weather system, which I find to be absolutely fascinating. So we do have a bunch of challenges that come in with this data set. So the data is big. So data storage is a problem. This also makes it computationally expensive to process. sensors differ. So there might be varying spectra between sensors. And due to this difference, we're not able to port models across sensors. So say in this case, the Himawari dataset has the green band, but GO16, we didn't observe green, we observed another band. So any model that we develop for Himawari 8 cannot be directly applicable to GO16 and 17. So this is kind of motivating one of their machine learning problems that we will talk about. Two of the other problems is taking into account geostationary with low Earth orbit observations and trying to actually predict one satellite from the other to actually improve this resolution synthetically. And lastly, I will be talking about a problem of atmospheric motion and wind. So wind is a very difficult variable to observe. And we've been doing some interesting computer vision work, looking at how we can get winds from sequences of geostationary imagery. So to go into a little bit more depth on geo versus LEO, and then we'll jump into the machine learning component after. So talked about the geostationary orbit. It's very high in altitude, and it has this period of 24 hours. So it's going around with the Earth, staying in that constant location. The low Earth orbit satellite has a much lower altitude. So this enables higher spatial resolution, but it also requires a multi-day multi-day frequency, right? So it's going around the Earth, say 30 times in one day. It's only going to see a given location once or twice for that day. So that's not a sufficient amount of information for, say, weather forecasting. We need to know it now or a couple minutes ago in order to do that forecast. But the data generated by a lot of these LEO satellites are really cutting edge and useful information. So if we can use these together in some way, that would be an ideal scenario for information content for things like, we'll talk about an example with land surface temperature. So the first problem I'm going to talk about is on virtual sensing and what I'll call spectral inconsistencies between sensors. So say we have 3 satellites, and all of these satellites have some set of spectra, some set of spectra that they're going to observe. And there might be overlap between satellites. So some satellites observe the same spectra. And then sometimes all of them will observe that same spectra. So the goal here is we're asking the question, can we generate all the spectra from any given satellite? So if you give me satellite A, am I able to generate these other 2 spectra that are coming from satellite C? And if we can, then we can harmonize all these satellites together and be able to use their models all as one. So I'm going to define this a little bit more formally here. So the question is, can we generate synthetic spectra to build consistent data sets across sensors? So if you're given these 3 sensors, we want to look at the union of all spectral bands. So what are all the bands together? And then for any given sensor, we want to generate all the bands that do not exist in that given sensor. So to motivate this a little bit further, we're going to look at this data set, this geostationary data set from GO16, GO17, which have the same specifications, and Himawari 8. So GO16 and 17, they observed the Ceres bands for measuring light clouds high in the atmosphere. And GO16, so GO16 and GO17 observe Ceres. And Himawari 8 observes the green band. So Himawari 8 can actually generate true color imagery. And we would like to be able to generate true color imagery from GO16 and GO17. So we'll show a approach that we take that allows us to actually generate this 17th band and true color imagery from the GeoNext L1G data. So we presented this approach, satellite to satellite translation, using, it's really based on an unsupervised image to image translation method, which uses a variational autoencoder and then a generative adversarial network to learn these translations between one sensor to the other. The idea here is that if we can learn this shared latent space that's consistent between multiple sensors, then we're able to do this translation almost for free and get these new spectra for bands that we had not observed before. And yeah, I'll kind of get into the loss a little bit here. So we used a generative adversarial network to discriminate between was this example observed or was it synthetically generated? And by using that loss function, we essentially ask our generators to generate something as close to an observed example as we can. And this is one way to constrain the VAE learning. So one question we had when we started looking at this to do a pretty thorough evaluation was, which bands are we able to drop and what terms do we need in our loss function and so forth. So one of the baselines would be, if we're looking at, so we have two satellites, we can remove bands from some of those observations and then try to kind of regenerate them, just like you do with an autoencoder or so forth. So we remove bands from the sensor, one band at a time, and try to reproduce it given the 15 bands. So we put 15 in, try to predict 16. One way to observe that 16th would be to take the overlapping example from another satellite. So we call that the cross sensor. So if we were to just blindly take a cross sensor observation, we end up getting pretty high errors. These are unreasonable for any sort of scientific application. So if we then look at, okay, we can train just a regular unsupervised image to image translation model without our extra losses and stuff that we put in, that does not work. There's too many spectra. There's too much dimensionality for the adversarial loss to be effective. So when we start adding in our terms and we get to this point, we're able to regenerate these bands basically for every band consistently with relatively low uncertainties. So this gives us some confidence that we can take out basically any band and we can replace it with a synthetic observation, and it comes out to be reasonable. So one of the next questions we then had was, okay, so how many of these bands are we actually able to drop? So I randomly took out bands that were less important, and we tried to see if we could reconstruct those bands given another set. So so this first example on the lower left right here is thermal infrared. So these are all the thermal infrared bands that we have. And I say, okay, I'm gonna only put in one band and try to reproduce all other 15 or all the 9. And we get pretty high errors as we would expect. Once I add in a second band, we're already actually doing a lot better than our cross sensor, which is kind of interesting. And then when we have, 6 to 8 of these bands, we're able to reproduce the remainder. So that's pretty interesting there to try to figure out. This allows us to ask questions about future satellite missions and which bands should we observe. Can we actually reproduce hyperspectral imagery in this way? And here's a couple of examples of imagery that we were able to generate. So Himawari 8 observed this true color example. And on the right, this is our Go 17 synthetic output. So it's really sharp. We're getting most of the variance there. It looks reasonably good. And in the same overlapping patch, we have GO-17 observes the Cirrus band. So these are the high clouds in the atmosphere that are actually important for understanding the reflectivity of solar radiation out of the atmosphere. And Himawari 8 does not observe this band, but we are able to synthetically reproduce it with our model. And this is what it looks like when we stitch together these three satellites. So what this is we have the Himawari satellite over much of Asia, and then the GO-17 and GO-16 all the way on the right. And I can replay this. And this is sampled every 30 minutes. We do have 10-minute data, but we sampled this every 30 minutes. And it really allows us to get this near global, real-time, consistent view of the Earth, which I think is really exciting. So the second problem I'm going to talk about now is on atmospheric winds. And this is part of a project that I'm leading as PI as a NASA ROSES project. And this is also on the theme of geostationary imagery and really taking advantage of the high frequency imagery that we have from these satellites. So observing clouds and their movement and their dynamics is of very high interest to atmospheric dynamics as a whole, and observing these at higher and higher resolutions is important for improving our forecast and our climate models and understanding the boundary layer. So observing these is complicated though. So there's vertical structure, there's spatial structure that we can see from above. So if we're looking from a geostationary satellite, we're mainly just seeing the top of the cloud. We're not really able to see this whole vertical distribution of the cloud, but we are able to see the top of it. And getting the direction of the movement of this cloud is important for initializing the physical models that are used to do the forecast. So in current forecasting, one of the main uncertainties in numerical weather prediction is winds, and is because that initializes partial derivatives in those physical models. And if we don't have accurate predictions of what wind and accurate observations of wind at basically every pixel, we're not going to be able to initialize these models well enough. So there are a number of applications for tracking atmospheric motion in these clouds. Some of these include, large-scale circulation, along with like pollutants and aerosols in dust storms, wildfire plumes. Is wildfire going to become more intense because we have maybe winds coming through, really high temperatures that'll really kick up some of the amount of burning material there. So observing these is challenging, and there's really not too many data sets out there with truly accurate winds. So we can sense winds in two different ways. They're basically two different styles or ways of remote sensing. Active sensing, which will actively send some sort of a signal down, maybe in this case, it could be a LiDAR sensor, which uses a laser to figure out, okay, how far is that cloud away, bounce the laser off of the cloud and measure the amount of time it takes to come back. So that's one way to get the height, right? And that's one way to measure what the movement of these clouds are. The European Space Agency launched the Aorta Satellite in 2018 to do exactly this, to measure 3D winds. And this is a low Earth orbit satellite. The results have been slightly questionable. There's still a lot of uncertainty in how strong that data is, right? So there's simply not a lot of actively sensed winds available. So the next thing that we have to try to look at is passive sensing. Can we use any sort of passive sensing techniques to get the most information about wind from our current data sets? And atmospheric motion vectors is one approach here, where we try to track the movement of clouds between a sequence of satellite imagery. So every 10 minutes, I have an image of where the cloud is, and I can look at the next image, and okay, let's try to find where that moved to. So this is done currently by some operational products, and they're used as major inputs to initialize these weather models. They're looking to measure the lateral and vertical movement of water vapor and clouds in the atmosphere. The features are quite challenging to track. Clouds they'll change in their form. We'll have physical processes from underneath where we get convection and so forth that'll change the form of the cloud. But current approaches use a pretty simple nearest neighbor dictionary lookup type approach, where we say, I have this current scene that I'm at for my current time step. And we go to the following time step and try to find a match. So try to minimize the error on some defined loss function that you have basically manually in going across and checking every possibility in that search window. This works if the features are very easy to track. As soon as you're in, say, low water vapor regions, regions where there's a lot of motion in the clouds, you're not going to be able to track it with this approach. And they found very sparse results and high uncertainties with this. And as you can see actually on the bottom right, they processed NOAA, this is a NOAA operational product of AMVs, and it's very sparse. So we only have winds in these areas where, it was easy to track. So there's a lot of the areas around the tropics where we have no wind information, and yeah, basically all around. So we would like to use machine learning to try to fill in these gaps and improve the accuracy of these winds. So one approach is to use optical flow. And this is a kind of a new way to look at atmospheric motion vectors. But optical flow tries to find the apparent motion velocities of movement of brightness patterns in an image. So if you're looking at rigid bodies in an image, then you want to track how far did that object move between these two images and get the partial derivatives in the X and the Y direction. There's two assumptions here. One is brightness consistency. So the objects in the image do not change in intensity between the images, and relatively small movements. So this relatively small movements you can kind of look at this as you're looking at the partial derivative of X in terms of delta T. And we know from everything to do with calculus, right, that we want that delta T to go to 0. So if our observations are as close together as possible, that's how we're going to get the most accurate partial derivative estimates from the optical flow. So this has been tried in a couple some of the numerical methods to optical flow have been published for AMVs in 2016, and then Jason Apke at NOAA is looking at this too for really kind of small scale examples. Our use case is we want to apply this globally, and a lot of these numerical optical flow models do not actually scale all that well to really, really high resolution imagery. So we're going to look at deep learning. So optical flow is deep learning. And this has been an area in computer vision over the last over the last few years that's getting a lot of attention, and convolutional neural nets are making some serious progress into particularly supervised learning of optical flow. So this model, FlowNet-1 was the original paper that came out using deep learning and optical flow, and it uses this multi-scale architecture where you output flows at increasing resolutions and apply a loss function over these different resolutions. They're trained mostly in a supervised fashion, so this does make it difficult to work with natural images. Natural images do not have the flows defined with them. When we take videos with the video camera, we're not getting the optical flows out. So we need to get labels in order to do supervised learning here. A lot of that is done using computer graphics, and there's numerous data sets out there that allow supervised optical flow learning for testing these. Unsupervised learning of optical flow is an interesting and I think promising area of research. It still would be probably considered an unsolved problem. We're getting much better results with the supervised method at this point. So we're going to propose an approach similar to what is done with the synthetic data coming out of computer graphics models, and use outputs coming from numerical weather simulations, or what we would call a nature run. So these nature runs give us simulated outputs of water vapor and winds. So we have these corresponding physically consistent information where we have a sequence of water vapor information along with the wind vectors in the horizontal and vertical directions. So we can use this information to actually predict the winds from the water vapor coming from the nature run. Once we train this model, we're able to apply it directly to our satellite imagery and apply. So we're able to generate winds or atmospheric motion vector flows directly from a sequence of satellite images of similar resolution to the nature run. And this, I mean, as I said, this is very similar to what is done currently in the computer graphics community. So I think this is a pretty interesting approach that we're trying to take here. So the application to the nature run, just to give a little bit of an idea of what this data set looks like. On the right is a couple images of what water vapor and then the horizontal and vertical winds. This data is at a 7-kilometer resolution every 30 minutes and has 8 pressure levels. So we built a training data set out of this, rescale the flows, and we'll test a few networks. So I'll move a little bit more quickly through some of these slides, I think, but here you can kind of see how our optical flow network looks digging a little bit further deep into it. So we have this 2 inputs for a specific humidity. We take a 512 by 512 patch, perform image equalization on that. So we normalize all the image intensities to a uniform distribution. Use our optical flow network to predict multiple scales of optical flow outputs, and then compare that with our simulated winds. And we use a root mean square vector difference loss to optimize this directly. And this loss is used pretty widely in atmospheric motion vector. The metric is used widely in atmospheric motion vectors for understanding uncertainty. We compared a number of methods as our backbone optical flow network to figure out how we should set up our network architecture. So at first I was interested in looking at this unsupervised optical flows. This proved to not work super well, and I'm actually still trying to get it working better. FlowNet-S, Mask FlowNet, and PWCNet all performed quite well. These are all in RAF. These are all different optical flow methods. We did end up choosing PWCNet, which uses a number of interesting correlation layers and cost volumes that really are able to improve our performance. So, I mean, we're able, in this one example here, we're able to get the wind vectors from these two tropical cyclones that are here, one in the Gulf of Mexico and then one in the Atlantic Ocean. So we can take these and transfer them directly to Go16. And when we do this, so unlike I show here images of an infrared water vapor band that I will apply this to. So we have a sequence of these. This middle example, this is what NOAA produces. So I showed an example of this earlier. And this is the AMV vectors from their model. And these are the optical flow winds that we're able to generate, along with a comparison of the NOAA AMV winds with ours. So we're able to get that really high correlation between those and fill in all those gaps that we do not see, where we see missing information from the NOAA AMVs. And we applied this to Hurricane Ida, which hit New Orleans in the United States at the end of August. And this is a pretty major storm. And just from looking at this example, we can see the eye of the storm very clearly. We can see the counterclockwise motion around the eye, and then the clockwise at the outer circle. And this is kind of the signature of a tropical cyclone. And we'll see it go right over through the city. In this, the eye of the storm is getting very, very small as it's going directly through the city. And then we can see it slowly dissipate as the storm goes on. And we're about another day out. So we'll look at a third problem. And this is for real-time land surface temperature. So we showed how we have these geostationary imagery where we're getting every 10 minutes, and then low Earth orbit satellites where it's come around every day or two. There's LEO satellites that can measure land surface temperature very, very well. And these models are not built out yet for geostationary. So our team has been interested to see if we could build models that can predict land surface temperature from geostationary by learning from low Earth orbit satellites. And we have a data set out that we've been sharing, Next AI LST. This work was done by Kate Duffy, and it's currently under review right now. But what we do is she takes Go16, and we get overlapping observations with the MODIS land surface temperature data set and cloud mask. We learn a convolutional neural net that allows us to predict land surface temperature directly from geostationary. And that output is our Next AI LST product. We're able to compare this across multiple sensors. So this plot on the top left here is our training pair, Go16 and MODIS Terra. The other three were data sets not used for training at all. Especially, so we used the Himawari satellite against MODIS Aqua. Himawari and MODIS are not included either in Go16 or MODIS Terra. That's totally out of sample satellites right there. And we're getting this very good correlation. So this does give us some pretty strong confidence in the output of our land surface temperature data product. And here we show that we're able to use this data set to track diurnal patterns of land surface temperature. So this box C down here, actually, so A and D. So A is the MODIS swap. MODIS is going to come around once a day, and it's just going to get basically this area once that day. And the next plot B is the geostationary image. So we're getting the whole region, slightly lower spatial resolution, but the whole region every 10 minutes. And we see that in this time series plot down here, where we have the MODIS observations as the open circles, and then the filled in the dot points are our predictions. And we're able to see this diurnal cycle of land surface temperature, which is really interesting and something we have not been able to look at before. And we've had a few publications in geostationary ML in the last year or so that you guys can take a look at if that's of interest. But I want to talk about just a couple more projects that we've been doing at NEX over the last couple of years, and just one slide on each that I think could be of interest to the community here. So one is some work I was doing on super resolution for climate downscaling, and we called this DeepSD. The problem here was that global climate models are very low resolution, and they're very computationally expensive to run at high resolutions. This is the same with numerical weather prediction outputs, and actually a lot of satellite outputs too. So we want to improve the resolution of Earth science data as a whole. So we developed a super resolution method, which was able to basically take in these low resolution climate models, use super resolution with elevation and topographical information to predict high resolution precipitation outputs from climate models. We extended this work a little bit further, and we did some Bayesian deep learning for uncertainty quantification on these outputs, particularly for non-normal discrete continuous distributions. Precipitation itself typically follows a non-normal, maybe log normal distribution. And most of the days it does not rain, but when it does rain, the rainy days follow that skewed distribution. So this work kind of looked at different approaches that we could take with Bayesian deep learning to quantify this uncertainty in climate downscaling. And lastly, this is some kind of exciting work that we were doing with using the quantum annealing computer at NASA Ames, and we use a quantum variation autoencoder to compress high dimensional imagery and high dimensional time series per search. And basically the way we do this is you can use a regular encoder, encode it to some latent space, and then we use the annailer to sample a true Boltzmann distribution and discretize it, and then we can use that to do our compression and our search. And this paper was published in KDD in 2020. So just some last thoughts on moving forward with AI and Earth science. So Earth observations and model outputs are complex, large, and heterogeneous. This is only going to continue to increase. We're getting more and more data in. Computing power is increasing, which is then increasing the size of the data sets that are being outputted. And these all need really strong data science and machine learning tools to deal with. AI provides this set of tools with accurate and efficient processing. So these are both important. I strongly do believe that building these AI models for Earth science does require close collaborations with domain scientists. I think it's pretty hard to come in directly as a computer scientist and take some of these either model outputs or observations and do something truly effective with them. I think there really needs to be this close collaboration between the two. And I mean, we're showing here that AI models are enabling us to produce novel Earth science data sets that people are of interest, and using these tools for both searching, compressing the data sets, and exploring these large spatial temporal data sets, which I think there's a lot of opportunity for in the future. And here's some links that you guys can follow up on if you want to reach out to me. You can email me at vandal@berry.org or thomas.vandal@nasa.gov. And yeah, you can find the rest of our information here. So with that, I will let that go, and I can keep sharing. I don't know, Udit.
Hi. Yeah. Thanks a lot, Thomas, for the fantastic talk and the fascinating works you are doing. So I would request the attendees to basically ask your questions in the Q&A section. I can see one or two questions. So let me convey those first. So Aday has asked one question. So it says, are deep generative models like GANs considered to be effective to build surrogate models for global climate models?
I think that not alone. There's interest in using GANs for various problems within, I think, earth science and climate modeling. I think that a lot of the issues here come into physical constraints, especially so on global climate models. We're interested in longer term predictions, and these are constrained by the Earth's energy balance, and many other factors. So including those into the modeling is where that challenge comes. So yeah, GANs would predict something, but it might not be physically consistent.
Okay, thanks. So I have another question from Ajay, actually two questions. One is, he thanks for the nice talk. And then he asks, what is your take on Planet Company commercially available with all Earth data for, say, agricultural and so on applications? Likewise, Starlink Musk company for internet. So that was the first question. And the second is there any way we can predict airflow or wind in future, say 60 days in future?
So, well, so in terms of the commercial interest, I think that's coming out, I think it's really, really cool. It's really awesome to see. I mean, SpaceX, for one, they're lowering the cost of launching satellites. So, I mean, that's just getting more satellites up there as a whole. A lot of the commercial applications, so Planet is one, the data they're observing is, yes, it's really high resolution. They're getting it relatively frequently, multiple times per day. And though the applications they're looking at aren't necessarily for weather and for climate and for things like agriculture, a lot of the Planet Labs work is looking at Department of Defense, intelligence work, because they're using just regular RGB imagery, basically, is what's coming down from there. And then, there's a whole bunch of other commercial companies that are coming up. This open questions about the quality of the data coming out of them, geo-registration quality, science ready quality of the data. Though we're sure there's going to be a ton of commercial interest in most of these data sets, and we'll make good use of them, I'm sure. And then, is there any way we can predict airflow and wind in the future, so 60 days? So I'm trying to work on predicting wind just in an hour. 60 days in the future is going to be pretty challenging. So I think that's the subseasonal forecasting problem that is just a problem in general. Like, let's look at even temperature 60 days in the future. That's an easier variable to predict, and we can't do that at the moment. So that's what I would say on that one. But I think that's an open problem too.
Okay, so we are quickly running out of time. So I have a very quick question. Let me ask that. So it's about your satellite to satellite image translation. So did you try to translate, say, from LEO to GEO, or rather the other way, GEO to LEO, so that you can have a better spatial resolution?
Yes. So we did that with that land surface temperature example could be considered that. So that could be considered a translation from the geostationary to the low Earth orbit land surface temperature. And then with that translation, we're able to generate that high frequency land surface temperature in that way. So that's one of the image translation examples that we have.
Okay, good. I don't see there are any other questions or raised hands. So I think Udit, you have raised your hands. You have any question? Quickly.
Yeah. Hi. Thanks, TJ, for wonderful talk. So I have one question. in earth sciences, specifically in applications in weather and climate, we are always looking for high quality benchmarking data. I mean, yesterday during my talk also this question came up. So and even for observations, we notice there is quite differences both in statistics and daily values for observations in situ as well as satellite products. So how do you navigate this challenge and while validating your algorithms?
Yeah, I mean, this is really challenging. I think that there's a problem. Yeah, this problem keeps coming up. So NOAA is talking about this too internally, where comparing, how do we compare models? So I have a little bit of a different view here. Is I don't really know if I don't buy that benchmarks are the problem. I have this view that we're all trying to, machine learning is a tool. There's been a bunch of work in the computer vision community and the machine learning community on benchmarks. They've done it on CFI, they've done it on all these other ones. I think the earth science community, the goal is now to let's unleash it on new problems. So if everybody's using the same data set, we get a benchmark data set, everybody's using the same data set. I'm slightly questionable about that. So, I mean, that's one, I guess that's one side that I see. On getting accurate, yeah, it all depends on the problem statement. So I'm always changing the problem that I'm going after, and it's never with the same data set and the same prediction, because then I'm just iterating on the same problem, and I don't want to be solving the same problem over and over again.
Thanks. Okay. Thanks a lot for the talk and also the engrossing question answer session. So we can move to the next talk. Thanks again, Thomas.
Awesome. Thank you guys so much.
Okay. So next we'll be having